Good afternoon. My name is Jim Fawcett, and this is the third in a short sequence of videos about Rust programming models. In this video, we're going to focus on the object model. The first video was concerned mostly with getting started, starting up, setting up the environment, and so on. Quick look at Rust code. The second model focused on ownership, which is a hallmark of what makes Rust Rust. In this video, we're going to talk about models, and lots of languages have object models. Most do. If you're familiar with C++, or Java or C#, you're used to using classes and using classes to build objects. In Rust, the model is a little different, but not that different. Rust doesn't have classes, but it uses structs in very much the same way that classes are used in C++. Structs can have composed members. These might be instances of language types, but they can also be instances of user-defined types. It can have aggregated members, and we get that by using the box construct. Box is a wrapper that manages data on the heap. And so, if we have a reference to something on the heap, that's an aggregation. And Rust structs have methods, just like C++ classes. We can give them methods. Methods are characterized by first argument in the method is a reference to self. And a self is a keyword in Rust. It's very similar to the C++ this construct. It's a reference to whatever instance of a type invoked the method that's being called. Now, when you call it, you don't pass that address, but unlike C++, in the declaration, we list this pointer. With C++, that's all implicit. Rust has chosen to make it a little more explicit as far as the declaration goes, and that's probably a good thing. So Rust structs have methods, and they also have something called traits. Rust doesn't support inheritance in the sense that C++ does. Doesn't allow you to construct many layers of inheritance with inheritance of implementation, but it has something called traits, which are very similar to interfaces, very similar to Java and C# interfaces. Normally, traits will declare one or more method signatures, and so any class that has that trait guarantees that it implements, and the compiler forces us to, implements those methods. So it's kind of a categorization of types into groups that are clonable, groups that are copyable, and so on. Traits can have implementations, just like abstract classes, and can have implementations in C++. And we'll see a couple of examples of that as we go. And it has access control using the pub keyword for public. So anything that isn't decorated with the pub keyword is private for all external uses, but any code in the local crate has access, in the local package has access to data, whether it's decorated with pub or not. It's kind of like the C# the C# internal keyword from that point of view. But anyway, so access control, if a method is public, it's available externally. to anything that imports that code. And within the package itself, everything is accessible. Okay, so traits are like a contract. They provide a specification, guaranteed behavior in the sense that these are methods you can call. It doesn't guarantee what happens when you call the methods, but it guarantees that you're able to call those methods. So, for example, and we'll show you that you can declare a function that accepts not a type but a trait, and that means that any type that implements that trait can be passed to the function, and the function will make use of that by calling the methods advertised by the trait. For example, any type that implements a clone trait can be cloned by calling clone function. Functions can accept arguments specified with either types of traits, and we're going to see an example of that. And this, accepting arguments by trait is a powerful mechanism. It's really dynamic binding, just like we do dynamic binding with virtual function pointer tables in C++. Same thing in Rust. Rust traits have an associated virtual function pointer table, and so we can do dynamic dispatch if we choose to. Okay, so if a type implements a trait, the trait methods become part of the public interface of that type. Methods can be called. And surprisingly, you can even implement traits on existing types, much the way that C# extension methods work. So if you look through a little sample code in Rust basic demos, you'll find an example of me using decorating an integer with a size method, because I'm having that integer implement the size method. So, we'll talk about that a little more when we get to it. Okay, so here's a sample of implementing them. So I have here's a struct, public struct. So it's a public, public will create publicly accessible instances, but its data is private. They're not declared as public. And I'll come back to this attribute in a minute. Here's a trait size, and so I'm declaring a function size. So this is a method because it takes the ampersand self. So when you call it, you'll invoke it with no arguments, and it's going to return a usize, a measure of the size in bytes of that object. And there's a function, a trait called show that I am implementing here, and this has a super trait debug. Now, you've seen me use it in the earlier videos. The debug trait allows me to display things with this placeholder that contains a colon question mark. This is a debugging format, and the model is that Rust knows how to format most of the things in its arsenal, tuples and arrays and vectors and maps and all that sort of stuff. It knows how to format them in a very straightforward way, intended to be used for debugging. And so my show method is going to use a print with this formatting specifier, and so I pass address of self, print. So I'm printing myself, using the debug. So I'm a struct, and so it's going to just print out a very uh, simple description of the struct. And I have now here, I have 1, 2, 3 traits that I'm defining here. I'm not implementing them. I'm asking the compiler to implement them, and it knows how to do that. It doesn't know how to implement all kinds of traits, especially my own custom traits, but there are a lot of traits it can implement. This particular struct is blittable. It occupies a hunk of contiguous memory, might be padded a little bit, but basically all the parts are there in one piece of contiguous memory. And I can do a memcopy and get a valid instance of that struct in some other location. So because it's blittable, I can implement a copy trait. Now, there are a few traits called marker traits that don't have any methods. They're there to expedite, to direct the compiler to generate code in a certain way. So for example, if I implement the copy trait, when I bind to an instance of something else, I say let x equals y, it'll just silently make a copy. It'll blit y's contents into this new location I've identified as x. It has to be type compatible, but so these are traits. And anytime I implement trait, the compiler wants me to also implement clone, and the compiler knows how to implement that for you. You might want to have your own special, clone computation, and if so, you can implement it yourself in the same way that you see me implementing this show function. Here's the implementation. So now I have this trait size without an implementation. So if I'm going to use that for test, I have to implement it for test. And here's the way you do it. Impl size, the trait, for test, for this type test. And, function size, use size, standard mem size of test. This is a standard library facility that essentially returns the byte count in the structure in this type. And so I've implemented that size test, and a lot of traits, they're just a line or two of code to implement them. Not all of them, but a lot of them. Now here's impl show for test. I have to implement it if I'm going to use it, but it already has an implementation. So I just say impl show for test, empty parens. This says just use the default. I'm happy with the default. I don't want to define a new function. So I could have defined a new function, but it's like accepting a virtual function, not overriding a virtual function. The same idea, in C++, we can do this by not overriding a virtual function. Same idea here. It's Rust's way of doing that. Now I can implement test. So I implemented traits for test. Now I can go along and implement ordinary methods for test. And so I want a construction process for test. So I'll implement test. All the methods that I want to implement for test can go in this block. They don't have to. I can have multiple implementation blocks, but normally we probably implement them all in one block. And so here's a public fn new self, and I just picked some silly values, x is 42, y equals 1.5, and so anytime I call new, it's going to have these values. It might have been more sensible to give this 0 and 0.0, maybe, you could argue, but this is just a demo, so I have I'm allowed to do silly things in a demo. All right, so if you don't know why I use this 42, sometime you want to go off and read The Hitchhiker's Guide to the Galaxy. All right, so that's implementing traits and methods. So, so the structure for all of this looks like this. Here I am statically binding the structure test to its methods. So I have trait show, trait size, here's the struct, impl, you know, all these are just statically bound. That means that at compile time, the address of these functions off in static memory is just bound into any calls that I make using this object. And I use some pointers. Actually, you can use pointers without getting into unsafe code. Uh, Rust has an unsafe construct to allow you an escape hatch from its typing system in those very, very, very few places where you need it. And for most people like me, you don't need it. You know, the library writers, when you're writing a concurrency library or something like that, you need it. But anyway, without using any unsafe, you can use pointers. You can't dereference a pointer, but I can use it to capture an address. And so I just, I made references to these various parts of the struct, and then I printed them out. I just displayed them. So I have a pointer to the struct, and here's its address. I have a pointer to the floating point. Here's its address. For the integer, here's its address. And the whole size of the struct is 16. These parts add up to 12, and the difference is padding, for performance and ease of code generation. The compiler is allowed to pad, provide some extra unused space. It's in this contiguous block, but it's all in this block. But anyway, that's static binding. Now things get interesting when we start thinking about dynamic binding. So let's for a moment, let's forget the diagram for a minute. Let's look at this function. Function size is some object of dyne size is going to return a size, okay? And I am just using that o.size function. So this says O satisfies the size trait, so I can use it. Now, I'm almost certainly doing some other stuff in this function. I'm just illustrating that I can use this function. And, if I just wanted to return the size in bytes, this does just fine. But the interesting thing is that I can pass in any type that satisfies that implements that size trait. So now I have what amounts to dynamic dispatching, because here I have, for example, in this block, let mut t test. So I'm creating an instance of test. I could have said use new. I just created it this way, which is okay. And now I say print size of t equals, here's where I'm using the debug format. Size is, I'm using that size is trait, I'm sorry, that size is function that accepts any type that implements that trait. So I could have a whole series of related types that I want to quickly generate their size. Size is a nice little facility. So that's dynamic binding. It's really polymorphism in action. Even though we don't have a fully formed inheritance hierarchy system like C++, it comes real close. And so anyway, so how does that work? Well, now this dyne really is a little data structure that has a pointer to a virtual method table. Okay, just like C++'s virtual function pointer tables. Has a pointer to this, but now it's the trait. Instead of having every type, every instance of the type have a pointer to the virtual function pointer table, now only this dyne object, when I want to use it, I pay for the price of that pointer. So now that pointer points to the table, and the table, goes to show and goes to size and goes to anything else that I might, have implemented for this particular type. I implemented new, for example, but the only thing I'm dispatching on are the traits. And so you know, the show trait and the size trait are the ones I implemented. So here's the real object, and Dyn points down to that real object and points to the virtual function pointer table. So when I pass this in, okay, the compiler knows it's got a Dyn object. It says, okay, the method, it uses this, the method is size, and the data that I'm operating on, it uses the data pointer and goes and grabs the data that I'm operating on to do what it needs to do. So really nice, nice structure. Okay. So harking back to the previous video, we talked about the ownership model, and part of that was copy and move types. So copies are types types that satisfy the copy trait are implicitly copied by compiler code. You know, when I say let t equal test colon new is copyable only because it's blittable. Remember that, you know, it's blittable. If I held a string, I couldn't do this because the string isn't blittable. But I've got all blittable elements here, all things that, you know, it's just in one contiguous block of memory. So now I say let t equal test new, let u equal t. I'm making a copy. And if I turned around and said t equals u, I'm assigning, I might have changed u, for example, after I made the copy. I can assign it back to t. This is now an assignment. This is a copy construction, okay, because I'm binding a new variable to this type t. And here I am assigning because I am, you know, assigning to this existing t. So value types implement copy and clone traits. Move types have instances that are moved instead of copied. You know, any type that doesn't implement copy is a move type, and the compiler won't let me implement copy for types that are non-blittable. Okay, so movable types can implement the clone if I want to. So so here, this happens to be a move type. Okay. I'm sorry, this happens to be a copy type. You know, here's it's allowing me to implement, allowing me to instruct it to implement the copy type. And remember, this is just a marker. It has no methods, okay? It's always called implicitly by the compiler code. You know, user isn't going to call copy on this. But clone is not a marker type. It has a clone method, and if I want to use it, I call it explicitly. And there's a good reason for that. Rust is making sure that I understand when I do something expensive, like making a copy of a long string, for example, the only way I can do it is with clone. And so you know, I'm explicitly aware that that's happening. I'm not silently making a copy under the covers. Okay, so, and here, you know, just like other languages, I have the layout. Here's my code for this test. You know, here's static memory. Here's the code for test. And when I implement these various objects, test 1, test 2, test 3, I have a self pointer. You know, so and there's a slot here in this test code for the self pointer, and only one. And when when I have called the method on T1, it sends its address, its self-reference to the code. And then when the code needs to mutate it, if it's going to, then it uses that self pointer to mutate it. And, you know, it's the same for other objects, but only one of them is active at a time. Okay, so comparing Rust to C++, C++ object model provides for composition, a very strong ownership relationship. Composed items lie within the footprint of the object. Aggregation is a weaker ownership. The object doesn't lie inside the footprint. The aggregated instance is not automatically constructed. It's only done when code in the aggregating object exit to, and it implements inheritance. Rust has composition. And remember, let's go back and look at this table. Sure enough, Y and X lie inside of this struct. You know, in the memory footprint of this struct, these guys reside there. They are compositions. And aggregation I can do using the box construct. I don't have an example in this for this video, but you know, it's quite straightforward. A box works very like a standard unique pointer in C++. And traits provide functions. They declare functions. They may implement them, but they don't contain any data. Some structs are copy, but many must be moved. You know, if I hold anything that isn't copy, any data member that isn't copy, doesn't satisfy the copy trait, then my struct will be a move type. Okay, one last comment. You know, we use these relationships, composition, aggregation, and inheritance to build interesting models. It turns out those 4 relationships are enough to model just about everything that we need to do in software. So this is a little example of a tool that might be tracking stuff going on in a software development organization. So, you know, we have people, properties of person. We have an interface for what, you know, things that software engineers do. And this was C++ was a abstract class. And here I have concrete types, developer, project manager, a team lead, and so on. And we can do exactly the same kind of thing in Rust, okay? I can have a person trait. I can have a person trait that has implemented some of the function. It can't contain any data, but it's implemented some of the functions. This guy could be just an interface, or it might have implemented, you know, some functions that might apply broadly here, and so on. So I can build these useful abstractions instead of having a whole lot of functions littering all over the place and data floating all around. I tie these together into these nice objects and have the objects that have domain-specific meaning. I can have these objects interact, and it's a whole lot easier to manage and build code. And the message here is that I can do exactly the same thing with Rust. I don't do it in exactly the same way, but pretty close. Same sorts of mental models, okay? With that, I'm going to stop for now. The next of these videos will be a shorter one talking about generics. So with that, I'm going to say sayonara.